Today, it's my pleasure to introduce Dr. Ryan Thalman from Snow College. Dr. Thalman received his BS in chemistry in 2007 from Brigham Young University before moving here to Boulder to pursue a PhD at CU. During his PhD, Dr. Thalman developed cavity-enhanced optical spectroscopy instruments for measuring various trace gases, deploying them on field and laboratory campaigns in Los Angeles, Cape Cod, the Pacific Ocean, Toronto, Canada, Manchester, Valencia, Spain, and the reaction chamber here at NCAR with John Orlando and Jeff Tyndall. Following his PhD, Ryan did a 2-year postdoc at Brookhaven National Lab with Jian Wang, during which he spent 12 months measuring cloud condensation nuclei in the Amazon as part of the Go Amazon campaign in 2014. After leaving Brookhaven, Ryan took a teaching position at Snow College in Richfield, Utah. At Snow College, Ryan teaches chemistry as well as a variety of other topics, including range management and forestry, natural resources, geographic information systems, and drone technology and applications. He is currently an associate professor and has been active in exploring research in rural air quality and instrument development in measuring trace gases. In addition to air quality, he has also been involved in the imagery of the Pando aspen clone, wildfire vegetation recovery, drone and rocket-based sensors, and community-based sensing. Today, Ryan will be speaking about measurements of gas phase oxidation precursors and products in the atmosphere using broadband cavity-enhanced absorption spectroscopy. Before starting, I'd like to remind the people following online that you can enter your questions in the space below the video at any time during the talk, and then at the end of the presentation, I will read those questions to Ryan. So with that, Ryan, the floor is yours.
Thank you, Kyle. It's a pleasure to be back talking to this audience in Boulder. Let me minimize my window there. So I'm going to talk about atmospheric trace gas measurements using cavity-enhanced spectroscopy today. Grateful to be with you. We'll get to all right, so let's talk about where we're going today with this. I'm going to talk a little bit introduction about atmospheric chemistry, what our big picture is. We'll talk about broadband cavity-enhanced absorption spectroscopy. We're going to look at some measurements of sulfur dioxide. And we'll talk about using an interferometer for detection of Glyoxal. And then we're going to look at some measurements of hydroxyl radical in the laboratory. And then we'll talk about some conclusions and questions. All right, so we think about the big picture of atmospheric chemistry. We have sources putting things out into the atmosphere, VOCs and aerosols, and we have different transformations happening to aerosols in the atmosphere. Our VOCs, our volatile organic carbon species, react with hydroxyl radical, which is our primary oxidant, that detergent of the atmosphere, to create further oxidation and eventually ozone. We have other climate impacts of particles and other, our big picture of our atmospheric chemistry in terms of our bigger impacts. We think about, from a regulation standpoint, we're looking at mortality, morbidity, and visibility. And so it's our big air pollution concerns in terms of public health. All right. The hydroxyl radical is the primary oxidant in the atmosphere during the daytime. Concentrations range up to 10 to the 7 molecules per cubic centimeter is typically what we look at as possible maximums during the day. We think about how is hydroxyl radical made. We have ozone is photolyzed, creating O singlet D, and some oxygen. We get that O singlet D reacts with water, and we get 2 hydroxyl radical molecules. And those go on to react with a variety, basically all hydrocarbons. All right, so let's talk a little bit about what's out there in terms of OH measurement techniques. We have LAF phage, laser-induced fluorescence by assay by gas expansion. So this is a power-dependent, laser-based technique, super sensitive. These have been around for a while, at least 30 plus years, in some form or another. You have chemical ionization mass spectrometry can measure OH. Reaction with isotopically labeled sulfuric acid is how that works. And then long path differential optical absorption spectroscopy. There is one of these instruments in existence. It is now permanently installed in the Jülich chamber in Germany, but measuring direct absorption of hydroxyl radical. So these are some techniques that are out there currently. in terms of what we're looking at, oh, actually we'll go back. There's some issues with these. The community's grappled with some interference from our phage instruments for, I mean, I'm remembering special working group meetings from 2012 around in that time, just trying to figure out what was going on with some different background interference. Because it's a fluorescence technique, there's power dependent calibration, and anything that absorbs or fluoresces, if you're pumping at 308, including a whole bunch of different hydrocarbons, can interfere. And there's some tricks in terms of their gas expansion to get around those, but there's been some trouble with that over time. SIMS, these are big instruments with high vacuum, some different problems with that. And then the long path DOIS just isn't available anymore. So we've got some limitations there. SIMS and LIF are super sensitive, high precision, but in the community, we're looking at something that might be a little easier to use and may give us a more primary measurement like the long path was when it was available in the field. All right, so what are we looking at for broadband cavity enhanced absorption spectroscopy? Looking to try to measure OH is where we've been going with this. We wanted a primary measurement using absorption cross sections. These are based on the fundamental electronic transitions. We want something that's lower cost, so it doesn't have turbo pumps, no dye lasers, things that get pricey, expensive, big hazmat concerns. But there's some issues with that, right? The short lifetime for OH, because it's highly reactive, means that sampling has to be done either at low pressure, like our LAF or SIMS, where you bring things in, you drop the pressure quickly, which increases the lifetime, or without an inlet, like the long path DOIS. So for us, in terms of cavity enhanced absorption spectroscopy, that means we have to get rid of the cavity in any inlet, and we've got to figure out a way to get sensitive enough in terms of how much light we're getting and high enough resolution to measure this at ambient temperatures in the atmosphere. All right, so many of you are in Boulder, and you probably have seen presentations with this before, but we will review briefly what broadband cavity enhanced absorption spectroscopy is, so BBCS. Basically, you have two highly reflective mirrors, and this creates an optical resonator. Any light that comes in, there we go, makes whatever light you get in proceeds to make many passes in the cavity, and some of it leaks out the end. And so you get long extinction paths. So if we're thinking about absorption spectroscopy and Beer's law, then we can make our absorption path very long, which allows us for the same amount of light to get to lower concentrations. In some of the things, normally in these, if you have an enclosed optical cavity and you have an inlet, you can use different gases to calibrate what your path length, your mirror reflectivity, or that base state of your cavity is by flowing helium or zero air or a known absorber. For open paths, especially where we can't insert something in flush, we're going to look at using a low loss optic as our known absorber or loss or extinction to calibrate what our cavity state is. Light exiting the cavity enters a spectrograph. We separate that out by wavelength. And we have this integrated light exiting. We're not pulsing the light in, even though that's what was shown in the graphic. The light builds up and continually exits the cavity. We measure this as a transmission spectrum relative to some reference. We get absorption. Okay. In thinking about how we calibrate mirror reflectivity, we look at how long the distance between the mirrors is in the presence of some absorber or in some sort of extinction. This is for the closed cavity where you have helium and nitrogen as your two gases. And this allows us to calibrate how highly reflective. Now this could be 98.5% reflective to 99.998% reflective, 4 nines. There's a wide range of this across different applications. For us, we're going to be looking at more toward 98, 99% reflective. If you have then that known reflectivity and you have a reference and your measurement spectrum, you can get out an extinction. This extinction then can be treated just like a DOIS retrieval. We'll fit a polynomial to any broad changes. Maybe that's the LED or whatever light source fluctuation or other things, other broadband extinctions, and we'll fit out our narrowband absorbers here. Now, this polynomial is also going to take care of anything that broadly redirects light, scattering or absorption. That could be aerosols, that could be any number of things could be taken up in this, but we are sensitive to that because any extra losses then reduce the amount of times that the light bounces back and forth between the mirrors, and then thus reduces your sensitivity. So that's one of your drawbacks and challenges with these, is trying to limit how much of that happens. Normally for trace gas detection, at where we have high reflective mirrors in the blue, green, or red, you'll put a filter on the cavity to remove any aerosol, so that limits your losses. You also don't get things sticking out and making things dirty. So the first step of this project, we wanted to explore then taking cavities down to the deeper into the UV. And this is a challenge because your available mirrors aren't as highly reflective, and they can't be because absorption, this dielectric coatings have large losses as you get into the UV based on the different coatings that they use. So our first step was then to explore, how can we get a cavity to work at 308? Do we have light sources that will work? Is everything going to go together? And so for this first stage of the project, we selected SO2 as an objective because we could, if we could make an instrument that was selected for SO2, there's an application for that, that aside from just where we're going with this, exploring cavities into the UV. And because, there's every year you get, somebody needs a deep UV LED for something, dental curing, whatever, setting your fillings. I went to the dentist this morning, no fillings, gratefully, but when they shine that light in there to cure your epoxy filling, those are using LEDs in the deep UV, water purification. All sorts of these systems in the industrial world are driving innovation. That means LEDs are getting better and better. And so every few years to revisit what sources you're using and see if something can be done now is a good thing. Our available mirrors at 308 nanometers are in the range of 98.5 to just under 99% reflectivity. So went after this. Now I teach at a 2-year college. I'm actually on the satellite tech campus, so I don't get the engineering students or anything, but I do have machine tooling and industrial manufacturing, and so some great partners in reteaching me how to use CAD, and we 3D printed all the parts for this to use a cage system to set up these cavities, which allows you an optical cage that sets most things in alignment. And so for this SO2 instrument, we had these triangular shaped cages with our cavity in between the mirrors, and see, the LED was down here, collimating optics, focusing optics, and our fiber on this end. So I've been doing a lot of designing, and we do a lot with 3D printing because it drops our manufacturing time, which has been super convenient and makes for good prototyping. All right, so when we think about our absorbing species at 308 nanometers, we've got a whole bunch of things. We've got NO2, acetone absorbs broadly. OCLO, doesn't mean we're actually going to see any. BRO, some short-lived compounds. Formaldehyde absorbs at 308 nanometers. And SO2 is down here and has a nice repeating, fine structure that we can fit and is very well defined, has a fairly strong 10 to the 18 molecules per cubic centimeter squared per molecule for our absorption cross-section. And so for these tests, and at the spectrometer resolution, we're usually working 0.5 to 1 nanometer. We chose SO2 as our test molecule. Okay, I'm not sure why I have oh, there we go. And so we set this all up, we got things working, we did some experiments, we sampled, overflowed some SO2 into an ambient stream. We're like, well, we do all this and measure SO2 in the ambient atmosphere, and the reality is that even though SO2 is a criteria pollutant, there aren't a whole lot of places that have a problem with SO2 and have enough to actually measure. In the state of Utah, I think there's only one actual station that still has an operating SO2 instrument because everybody else has been so far below the the NaAQS level for so long that we don't have to measure it anymore, which is a good thing. So I had two instruments, a Thermo 43C and a 43I, that were available for measuring SO2, and you can buy SO2 as a standard. And so we use this to look at our absorption. So we overflowed some SO2 into an ambient sampling stream, and then we just went through and sent it through the calibrator and looked at our comparison between our different techniques and did some averaging and looked at what we could do there. And it performed quite nicely. All right, and here's some of our fits, in the range of half a ppb, 10, 40, across a range of SO2 values. All right, now SO2 detection techniques. This is a flash photolysis fluorescence technique that the flash lamps are in the 270-ish nanometer range. So it actually has some interference. NO will interfere, will also fluoresce. Some of your hydrocarbons, benzene, your aromatics will fluoresce, which is a similar sort of issue that you get with LIF for OH, actually. And so we tested this. We put some NO in there. So you can see here's our NO detected by the Thermo Instruments 43I, and we don't see it at all, which is great. So we've got fewer interference than some of our other SO2 techniques, but we also want to say, okay, we're eventually trying to get to an open path where we take the tube out. That means let's measure some SO2 in the presence of a broadband extinction. Now, at this point, like, we could do aerosol, trying to get aerosol with an open path or an aerosol generator. I said, well, we've got plenty of other broadband absorbers, so let's do that instead. And so we supplied some xylene because that was one of the other absorbers that interfered with our other SO2 instruments. And then we also just added acetone, which has a nice broad featureless absorption spectrum like we saw on the previous slide. And we see no effect on our SO2 signal, which is great. So we're insensitive to these broadband absorbers. This is just, we estimated our acetone concentration just by what's the value of the fitted polynomial. The only broadband loss should be acetone, and interpreted that as, well, this is basically absorption due to acetone. And we could have gone one step further and turned that into a concentration, but we can see the acetone comes in and our SO2 signal and our retrieved concentration is unaffected. Okay, so our conclusions. So even with fairly low reflectivity mirrors, 98.5%, our sensitive detection can be achieved for species in this wavelength range. So that's great. We've got the light sources we need. The mirrors are good enough, and for this detector, this worked. Newer LED light sources are expanding the ability to measure compounds at shorter wavelengths, so this is a good thing to do. And detection was insensitive to broadband absorbers, as well as other interfering species for other SO2 detection techniques. And we're able to get down to into the PPT range for SO2. So if somebody wanted to do this, and could use broadband cavity enhanced absorption spectroscopy to measure SO2. This was published in Sensors in 2022. That's the QR code, takes you to that paper if you're interested. I'll leave it there for just a second. So we've got our first part. Can we use an optical cavity at this range? All the stuff I did in graduate school, we were working at 3 or 4 nines in terms of our reflectivity, so much longer absorption path lengths. You only get maybe 100 passes in terms of the amount of times the light bounces back and forth before it has died off in these low reflectivity cavities. So we needed to see, well, can we do it? What actually will work out in this? So this was successful. Okay, so we're going to look a little bit now at formaldehyde and glyoxal. So both formaldehyde and glyoxal are short chain hydrocarbons with aldehydes, and are significant products of oxidation of lots of different VOCs in the atmosphere. Both have strong UV vis absorption spectra, which can be used to get sub parts per billion detection levels. And so this is good. We want to understand atmospheric oxidation. let's explore a little on the OH on the oxidizer end of things, and let's look at some of the products. The ratios of these two oxidation products combined with information about NO2 has been used in the past to understand information about the sources of VOCs in the atmosphere. Are we looking at anthropogenic sources? Are we looking at biogenic sources? And so these are good indicator species. Formaldehyde is pretty much a product of oxidation of every single hydrocarbon in the atmosphere. Because it's a one-chain aldehyde, you're adding oxygen when you add OH, you're going to get formaldehyde of some sort. Glyoxal comes from different sources. You can get it from some anthropogenic sources, other biogenic sources. The time I spent with John and Jeff down in the lab at NCAR was looking at isoprene oxidation, and we measured glyoxal. So, and looking at those formation pathways and reaction mechanisms. Okay, so these are interesting compounds to measure, and so thinking about other things that we can do with optical cavities and some different detection techniques, and so we were going to explore some of this. Now, detection of compounds by cavity enhanced absorption spectroscopy, these can be detected also by satellites, long past DOAS. LIF has been used for these, and a fairly large number of techniques. Broadband cavity BBCS is especially helpful. It's an in situ measurement. It is insensitive to interferences because you measure a unique fingerprint, and so of that compound at that set of wavelengths. So you can't get something else that you could compound onto the signal and misinterpret because you have a distinct absorption cross-section. Okay, so what we wanted to do is we said, well, let's look at some different ways of treating absorbers, because usually what ends up happening is when you're building one of these instruments, your mirrors run you a grand or two. You've got all your other electronics and everything, but the biggest sticker price is the spectrograph, right? So you can look at some lower end USB capable ones that'll run you $15,000, or bigger, nicer, cool detectors on your CCD, and you're looking $70,000 to $80,000, $90,000. And so you're like, okay, well, that's pretty expensive in terms of an instrument that you may want to deploy many of these. So we wanted to look at some different ways of detecting compounds that could change how we look at those absorbers. So we said, let's look at an interferometer approach. Okay, so we built this setup. We put in a bifurcated fiber. We took some of the light over to a spectrograph where we could look at what was coming out of the optical cavity, because we still want the optical cavity because we want a long absorption path. That's what's getting us our sensitivity. Okay, and so now looking at what's happening to the light coming out of the optical cavity, we said, well, let's put in something that allows us to change between two things, like an interferometer, at two bands. And so what we did was we put a bandpass filter here. And what's interesting about sputter-coated bandpass filters is that when you tilt them relative to the incoming light, the range of transmitted light changes. Will shift to shorter wavelengths as you go away from a 90-degree angle of the incident light. And so we took basically a servo motor off of a radio-controlled airplane in a little cage, and we allowed this to turn and go back and forth between two positions. The light coming out of here was sampled by a photomultiplier tube, and that went into a photon counter, and we got a signal out that looked like this between an on-band and an off-band position. On the next slide, we'll look at a zoom in of this. So we were able to supply some Glyoxal in this case, and then also put some NO2 on top to look at what would happen, one of our normal major absorbers in the 455 nanometer range that might interfere, make this not work. So here's what this ended up looking like. Here's our absorption cross-section for Glyoxal in red. We have our on and off band positions for our bandpass filter, so that's where the light was being transmitted, and trying to get them far enough apart from each other to have at one point you're sampling Glyoxal, the other you're sampling the background under similar conditions. Here's NO2 in the brown, and actually methyl Glyoxal here in green as well, which is more featureless, especially at these wavelengths, and has a weaker cross-section. So what we did then was we looked at the intensity of light so let's see, 458 is the off-band position, which would be some contribution of Glyoxal and NO2, and I'm wondering if these numbers are backwards, but and we know something about NO2 is only at 458, and we could then retrieve from the extinction at 455 the concentration of Glyoxal, and you can then iterate back and plug in your Glyoxal to kind of account for maybe there's a little bit of absorption. So we did an iterative approach on this, assuming 2 absorbers. This is what our reflectivity curve looked for this. It's 99.985% reflective, and a really nice sample of a reflectivity curve. And so this is what some of our CCD, our data from the spectrograph in CCD looked like. Here's our Glyoxal, here's our NO2 at another point. Quite nice fits, just look beautiful, just very sensitive to those. So our experiment we set up, we stepped through a variety of concentrations of Glyoxal by bubbling through a Glyoxal solution. And so here we have Glyoxal, here's our steps of different concentrations, and we brought down back here to one of a slightly lower concentration, and then introduced some NO2 at a variety of concentrations as an interferent. What we found was somehow our Glyoxal stock solution we bought had a bunch of methyl Glyoxal in it, which was interesting, that grew over time as the solution got older and older and we bubbled through it more. We also measured the water concentration, water content, because it was a solution. You can also measure water, but that didn't impact our interferometer measurements. So we have nice sensitive detection here. And so this is what our data comparison between the CCD and the interferometer looked like. Here's our NO2 in blue from the 2 instruments, and orange or brown from the 2 instruments. Our Glyoxal in red and green. And actually there's 2 different interferometer settings, this gray, using a different way of, at one point I tried, let's just use our measured NO2 and plug that in and see how that comes out and compare that to if we were measuring the NO2 from the interferometer. And yeah, it's not great, but we see our steps of Glyoxal. We can actually use an on-band, off-band detection to look at narrowband absorbers like this, coupled to an optical cavity. So we have our optical resonator, and then we have something that's chopping our light on the way out. All right, so our combination of an interference filter with an optical cavity can be used for narrowband absorbers. So this means that you could tie a more conventional detector, a photodiode or something, PMT, to the end, and use that even with the light exiting these cavities is pretty low. So if you have something that's 99.98% reflective, 99.98% of the light gets thrown out and bounced back from the LED before ever entering the optical cavity. And so you're working at fairly low light conditions. That's why we're normally using a CCD, and we're integrating for longer times, and you want a cool detector, all those sorts of things. But we can make this work with an interference filter of some sort and a PMT or perhaps a photodiode. For our CCD, our detection limits for Glyoxal were 10 parts per trillion for a minute, and 22 for NO2, and 34 parts per trillion for methyl Glyoxal, which turned out quite nicely. I think this is better than the stuff I did in grad school, which is awesome. Our detection limits for this setup with the interferometer at 2 minutes were 600 parts per trillion for Glyoxal, 900 parts per trillion for NO2, assuming that NO2 was that absorber at 458 nanometers. So there's plenty of room for improvement. Obviously, these don't, this is not as good as using the spectrograph, but this is a different style of measurement. This is going to use different equipment. You don't have to rely on a CCD, some sort of spectrometer on the end to do your fitting. This was published in Toxics this year. There's a QR code if you're interested in looking up that paper. There's plenty of room for improvement. We were not optimized on how we were using the PMT, and we just ran the photon counter output into a LabJack DAC. So absolutely not optimized. I think there's room for at least 2 or 3 times improvement just from the electronics end of things with the same detector. So plenty of room for improvement, but it worked. And we're thinking about just where are hydrocarbons in the atmosphere, different oxidation schemes. Finding different ways to measure those are important. In terms of VOCs, some people look toward metal oxide sensors, which have huge interferences, large drifts, highly affected by humidity. We've got drawbacks and challenges with each type of measurement, so introducing a new type of detection scheme is a useful tool in the toolbox. Okay, so we've done some different things that we're combining and looking at in terms of optical cavities and how to measure trace gases. Now looking toward going to our open path, we need to remove that inlet for OH because it's short-lived, and looking at our field prototype. So this is a proof of concept. We're still going to use SO2 as a surrogate molecule to start because it's easy to supply. You can get it in a standard cylinder. We'll look at, well, how does this work with aerosol? If we're going to go outside, we've got one of the things we're going to move to is that in this open path, we're going to start to move the mirrors further apart. Because we have low reflectivity, we need to increase that base path, the distance between the mirrors, that so for our given number of passes that will stay roughly the same, we get a longer absorption path. So we'll be putting these on tripods in our open path configuration. So the first place we did this was we put it in this Teflon bag. In our simulation chamber, you can see the UV lights up on the top. And then we're going to apply this to OH radical. And then we're also going to, we want to measure a narrowband absorber. That was the thing, like 0.5 nanometer is not good enough. We want to go to finer resolution. And so we actually want to supply something that has highly defined fine resolution absorption. And so we actually used flame as a source of OH. And there's an example of that on the bench top with our mirrors and just a couple of little flames, and trying to get that some high resolution spectra of OH, even if it's not at the right temperature, and we'll see some more about that in a second. All right, so here we have our experimental setup. You've got 2 tripods. 5 meters is our radius of curvature, so that's where how far apart we can set them. So from a 1 meter to a 5 meter pass, that increases your absorption path by roughly 5 times. And in these boxes, you've got a plate and all your optics mounted. You can purge and flush out, so we keep all the aerosol and dirt and muck out of there. Our light shines through the cavity, exits the cavity, and is collected. And we had to do, because this is a 1 meter McPherson spectrograph, this thing weighs like 600 pounds. That was sitting around at my collaborators, and so we got a CCD for it, brought it into the 21st century, but it's an F7, and fibers are usually in the range of F4, so we needed to recollimate that light. So there's a cage hanging off the front of this, and brings the light in at F7, illuminating the slit on the spectrograph and getting resolution. We can usually resolve 80 picometers at best, full width half maximum. At 98.5% reflective, we get somewhere in the order of 70 passes between the boxes, between the mirrors, but without trying to, with a fairly broad source, collimated light going through. Okay, so we're collimating the light in the back of the mirrors. We're chopping the light down to make sure that any light that ends up in the optical resonator and gets to the fiber at the end actually went through the cavity instead of leaking around somewhere. And inside this box, this little switch here controls a motor which drops your low loss optic in front of the lens so that we can calibrate the mirror reflectivity. So here's our survey tripods set up inside with the boxes on top and the optics all mounted in there. Okay, so we did some tests. We want to know, to understand, okay, so we'll put in some aerosol losses. We're going to measure some aerosol. We're also going to turn on a fan because, in the real world, air doesn't move in a laminar fashion from one mirror to the other unless you control it. And so we wanted to understand, like, if we increase our turbulence, so we put a fan in there to blow the air around, can we still fit things? How does it affect our light? Do we see a light loss? All that sort of thing. And so we put some aerosol in. There's a big spike of aerosol here, which was very big. Here we put in the loss optic, which messed up our fit, but that's okay. That's what it's supposed to be doing. And we turned the fan on and off at different points with aerosol, with varying amounts of aerosol in there. And we saw very little effect to our fitted SO2 retrieval. So we're insensitive to our turbulence, which is good because if we take this outside, wind's blowing around, we need to make sure we can, that this doesn't provide an additional loss. Okay, so moving to this, we also had our previous work with SO2, and our turbulence testing, we did this at 0.5 nanometer full width half maximum resolution in the spectrometer, but we needed to go to something better than that because OH has finely resolved features, and when you go to finer resolution, if you can still maintain high throughput, you get stronger absorption cross sections. And so we have this McPherson spectrograph. It's a 1 meter Charney-Turner spectrograph coupled to a Hariba CCD as the detector. Light had to be coupled, as I said, into the cavity through a telescoping lens, set of telescoping lenses to get the light entering the cavity at f7 so that the imaging to the chip worked correctly. Optimized, we were about 80 picometers at our best resolution. All right, so we wanted to try to do at room temperature detection of OH. We tried a lot of different ways to do this. We tried photolyzing hydrogen peroxide. We tried photolyzing water. We tried photolyzing ozone in the presence of water. We tried photolyzing HONO, nitrous acid, and we just tried reacting an alkene with ozone to make OH. Through this, we had a variety of different setups, from in the bag to something set up between the tripods with a box between the mirrors, to something on, that box moved to the bench top, to a flow cell that was 1.5 meters, to something that was 2.5 meters to 5 meters, a variety of setups. And we kind of failed at all of them, which is annoying, but there's some reasons for that. In order to try to make enough OH to measure, considering its lifetime, you have to pump in a lot of stuff. Hydrogen peroxide absorbs at 308. In fact, it absorbs so much, we put so much hydrogen peroxide in that we lost all of our light between the mirrors. Water, you have to photolyze down below 200 nanometers, and we just couldn't get lamps down there to do it, and we didn't want to try to pump some laser through our big bag. Photolyzing ozone also absorbs, and so we lose light there, and depending on how much then reacts with other stuff or the walls, we didn't get there. HONO, getting a stable source, proved to be difficult, and we did a lot of work on that, and that fed into a different project, but we didn't get that tuned, and then it also makes NO2, which absorbs. Reacting an alkene like 2,3-dimethyl butadiene, I think is what this is, or tetramethylethylene is the other name for it. Plus ozone, it efficiently makes OH. The problem is that it makes a whole bunch of other stuff too, including formaldehyde and acetone. And so lots of different interferences. This just didn't end up working out with what we were doing. So here's just one example of this. Here's TME plus ozone. This was done in a flow cell. So we provided this TME, which you couldn't measure, but then you got an estimated from our polynomial ppm levels of ozone, or not ozone, of acetone, which degraded how much we could actually measure of anything else, but also created nearly a ppm of formaldehyde as well. And here's our fitting no ozone, or no OH. It also reacts fairly quickly, so now we've also provided a whole bunch of other stuff for OH to react with around it, which can prove challenging. Here's a fit from this. It's a beautiful high-resolution fit of formaldehyde. It's great, but no OH. So we said, well, we want to do something that's high resolution, that really resolves at that 80 to 100 picometer resolution that we can get with the spectrograph to test what do our fit parameters look like for OH. And that's what we wanted to get after here. And then what does that mean that our detection limit will really look like for OH? And so we said about, okay, let's do this with a flame, because OH is made in the flame, and we can get some of that to end up in our absorption path. Now, there's some challenges with that again. So these absorption lines were extracted from Hytran and the cross sections were generated using HAPPY, which is the Hytran something. It's a Python build on, which works actually quite nicely. And so here's 296 Kelvin, kind of the standard one we're used to at 90 picometers was what I was convolving these two. Here's 800 Kelvin, and here's 1800 Kelvin. And right between 1500 and 1800 Kelvin is usually about where the flame temperature is. Now, You'll see how these fits look in a second. But you'll notice that as you go to higher temperatures, this band here at 309 gets more intense, and the more intense bands at 308 drop off, and actually at 1800 Kelvin, our absorption cross-sections are roughly half at this resolution of what they would be at room temperature, which we can use. We want to understand our fitting, some of our fitting parameters. We want to look at high resolution fitting. What does our window really need to look like? As we move off of 308 over here towards 306, we start to lose light. The LEDs is somewhere at 308 to 310. We're just losing light as we go down here, so we're going to end up in a poorer regime because we've got fewer photons. So here's some examples of this. We put and move the flame down. You step the flame down lower in the absorption path to access different amounts of OH in that absorption path. And here's an example fit. I think that's somewhere right down in here. I have a pretty nice fit at 2.5 meters base pass, but the flame, is 1 centimeter of this, and so it's averaged over the full absorption length of 10 to the 12 to 10 to the 10 molecules per cubic centimeter. A fairly wide fit, looks pretty nice, a nice looking residual. And in this, we had some degradation in our mirror reflectivity. Things had gotten dirty, but still able to measure it fairly sensitively. Here's another example, much lower concentrations. Here we're in the 10 to the 10 range, and this is what our fit looks like, which actually fits quite nicely. Our residual looks beautiful. So a success, and definite measurement of the OH relative to our reference. We came back to the flame being off here, came back to it, 45 and 50 minutes later at these concentrations, which is nice. Now, in the atmosphere, we can do things like, we've got all day. As long as we have a white noise sensor, we can average to an hour and get our hourly average OH over time. We've done this with formaldehyde successfully at 350. That was, using some mirrors I borrowed from Rainer Fulcomer back in the day. We measured formaldehyde in Bountiful, Utah, way off the mirror where it didn't belong. The cavity should have never been used there, but we got it to work. We got 1 part per billion. But we averaged to get there, and it worked successfully. So we can use this as a white noise sensor because of the CCD and our multiple channels. Okay, so one of the other things we explored with some of our colleagues at BYU was a Gauss-Hermite filter, which is a discrete Fourier transform of the signal to frequency, and it ends up being a sophisticated low-pass Fourier filter. So we can separate out high-frequency noise from the low-frequency signal, but you may result in some losses of resolution being too aggressive. So you can tune this filter to say, okay, well, how much noise do we want to remove while maintaining our resolution? So here's an example of that. This is a lot higher amount of the flame here, but we want to say, okay, at this resolution, how does this filter perform? Is this a tool we could use in doing our fitting? And so now, one thing to note is these flame cross-sections, flames flicker, so concentrations vary widely. But also modeling them proved challenging. At first, we started using a program called LAF Base out of Stanford, which has been around a very long time, which would give us our absorption lines, but didn't actually give us values for the absorption cross-section. Going back and using Hytran, we were able to finally figure out how to get the temperature where we wanted it and get those out. We got those calibrated. But the lines don't always match up for what temperature you think the flame's going to be at. You try a variety of different. We tried fitting multiple different temperatures to see if we were getting part of the flame at one temperature and part of it at another, which was causing some of our issues with our fit. Like this, for instance, this peak right here shows up clearly at 1800 Kelvin. This is supposed to be here. It was never there. I'm still uncertain why. And so there's some challenges with the flame. You have your flicker noise, changes in temperature, but the filter decreased this noise by 2.5 times. Now, this looks like not as good of a fit, but that's what when you reduce the noise and you change how this fits, you're going to get some different issues. But we can reduce that noise by 2.5 times by using this filter, which is a valid tool in our toolbox for how do we go forward and decrease our limit of detection. All right, so that's been our explorations in measuring deep in the UV at high resolution as we're trying to get an instrument that we can deploy to measure OH in the field. Our 1 hour detection limit in the lab, currently we're gonna stand by 10⁻⁷ molecules per cubic centimeter based on our light throughput and other things. We can get to this level as we average to an hour. Now, obviously, we're not quite to our ambient levels yet. Now, our filtering reduced our noise by 2.5 times to this level, which is great. That's a pretty big jump. We can quantify our interference. If there's high resolution formaldehyde or some other things, like some formaldehyde or other things, we can fit those out. SO2, HONO does absorb there. I don't think we'll ever see enough HONO to actually measure. NO2's not very sensitive, but if it's there, and I remember watching a talk, they're talking about, ppm level of NO2 in Santiago or something like that. And you're like, okay, I guess we could do that. Pretty sure we'd lose all our light anyway because of how much aerosol would come with that. And then formaldehyde as well. We would consider this instrument as built semi-portable. As a pretty large spectrograph, I'm sure we could, somebody could invest in a better, smaller setup spectrograph that could get similar resolution. We liked the McPherson. It has high throughput, so we get a lot of light through, a nice CCD on the other end, and we had the spectrograph in the lab already. We just needed to put a new detector on it. All right, but we have lots of room for improvement. Better collimation. Currently, there's a big light loss going from 2.5 to 5 meters that I think we can improve on drastically. So if you double the path, double the absorption path, but if you have any beam expansion, you can lose 4 times the light. And so some things we're working on and that are currently being improved. Other optical throughput light issues, coupling into the spectrograph, optimization of the LED, some different things that we're working on that are getting us closer to where we want to be. All right. So in our future work, we're going to test our field deployment for ambient detection of OH. Let's see how this works. Let's test our tripods outside, not just in the bag. So this will include some of our light throughput improvements and platforms, so our alignment of our boxes and any stabilization that we might need to do. So other projects kind of related to this work, we have a dual cavity instrument measuring Glyoxal and formaldehyde that's deployed in Provo at Brigham Young University. That formaldehyde instrument has a limited detection of 450 parts per trillion, which is really good. And our Glyoxal instrument, just like we had used in that part of the talk. We will also be participating in the NSF project verification of atmospheric mercury redox rates this winter, depending on where they end up sending us as we figure out that field deployment, but that's what's coming up for us. I really want to acknowledge my co-authors on these projects, Jaron Hansen and Matt Asplin, professors at BYU. Callum Flowerday is the graduate student who has done a ton of this work, has been super productive. Just an amazing worker, has just been dove in and learned a ton. And I mean, at this point, even just this instrument development and just in atmospheric chemistry in general has been super productive. The SO2 work was originally funded by the Utah NASA Space Grant Consortium, some research seed funding from them for that project. This OH work has been funded by the National Science Foundation. I'm here at Snow College, which they put up with me doing research, even though we have a full teaching load. And I try to get my students involved as much as I can. And BYU supporting my collaborators in space and all the great things that we get to do in this. And so with that, I will turn the time over to questions.
Thanks, Ryan, for a really great talk. So we've got a couple questions and comments up already, and then if people online, again, enter your questions into Slido, and then I'll read them to Ryan. So there's a comment from Ale Franchen, very interesting, great talk. And then there's a question from Changming Chow. Great to hear another radical instrument. Doesn't OH emit any fluorescence at 308 nanometers?
It does, and that's an interesting question that probably need to look into more. One of the realities is that in our optical cavities, we cut out most of the light. So we should mostly be dealing with absorption and not actually pumping the OH. But we could look at that and explore what that might be. But the reality is we're not actually putting in that much power through the optical cavity. So.
There's a comment from Romulo Cruz, who's a grad student in the Volcamer group and who's actually using your instrument, Ryan. He just says, very nice talk.
Thank you. Hope it's working well.
So I have a question. You mentioned earlier that some of the halogen oxides absorb down in that same wavelength region, and those are also very reactive species that don't like inlets. Have you thought about when you do the field deployment? I mean, you're right by the Great Salt Lake. Have you thought about if you're going to see that and how handle that analysis?
Yeah, so for BRO, there's better wavelength ranges to do that, and we will be putting an instrument out there that could measure some of that if there is some at 350 nanometers. The problem is that we're looking at absorption paths maybe up to 700 meters, which is still pretty short in terms of these other absorbers. Let me think what, where's my cross sections? Okay. These are nice and strong down here, but we would need so OCLO, the challenge would be we need a wider window. And usually if you're trying to get your bandpass filter and depending on the resolution we're working at, this might be a challenge here because it looks like you would need probably, 10 nanometers instead of 2 to fit out OCLO quantitatively. BRO you might be able to do, but you might be limited by the fact that there's better places to try to do that. But I mean, if there is some and then we'll look. And if the nice part is that these have nice structures, and if you start seeing something, then you add your cross section in to fit it out once you see evidence of it. So. Does that answer your question, Kyle?
Yeah, thanks. Do we have any other questions from the folks online? Give it a few more minutes. So I'll ask one other question.
Okay.
So typically for these cavities, it's all machined parts. With the 3D printing, how accurate were those prints? Did you have to go and, modify stuff later, or is this something that for laboratory systems is viable with the new printers?
I mean, to be clear, I printed all of these on an Ender 3, which is a $180 3D printer. So I printed it on a low-end printer. There's some work to be done. So you have to go in and tap screw holes through plastic, which is not great. Usually I'd have to take a 3/8 drill bit and drill this out and open it up a little bit so it'd clamp on the tube. There's some after machining to do, but it's been quite reliable. They're a little floppier maybe than a machined aluminum part. But once you put them in and you leave them and you don't touch them, they stay. And so a group at the University of Utah has used a formaldehyde instrument I built for them, looking at low cost sensors, and used this as their primary measurement. So and has been successful with that. I've gone back to a square. It just was easier to reach my hand in to adjust things. But there was some issues. Like, one thing to note with this is 3D prints aren't very airtight. And so what I ended up doing is coming in with a metal tube in the end and meeting that to a metal bushing as my seal instead of trying to get the 3D prints to seal. So it's a combination of things, but using them to get the structural optical alignment set up is pretty nice, which is what you guys have all seen with cage systems at NOAA, for instance, and others. So I did want to note, moving to the 5-meter base pass, we went to 2-inch mirrors, and that's one of the things we've been doing more is trying to make use of these larger optics because your collimation effects are better. The challenge with closed cavities with 2-inch mirrors is that your flows are really messy and don't like to, like, your turbulence, things don't want to flow where they want to. So if you're really working with flows, 2-inch mirrors, 2-inch cavities are actually quite challenging. So.
Looks like there aren't any other questions online, so let's thank Ryan again for a great talk. And then our next seminar will be in 2 weeks on August 8th. It'll be downstairs in the big auditorium given by Sewon Kim, who will be discussing exploring Korean air quality using chemical transport models and multi-platform observations.
Thank you,
Thank you,
Kyle.
everyone.
Thanks everybody for coming.